this video, we are going to discuss about types of dynamic CMOS logic circuits. So, the dynamic CMOS logic circuits are classified into two types based on the use of the transistor to control the discharge path to ground. The first one is footed dynamic CMOS logic and unfooted dynamic CMOS logic. So, first let us discuss about footed dynamic CMOS logic. Here, the NMOS transistor is called as footed. So, I have represented in the dotted line, you can see. So, it is added in between the evaluation network, that is below the A that is connected to the NMOS, right, and ground. So, the footer transistor is controlled by the clock signal. So, for the gate, I have given a clock signal for the footer transistor. So, what happens during the evaluation phase? So, during the evaluation phase, during the pre-charge phase, the clock value is 0. So, the VDD value will reach the output. So therefore, under the clock, since the clock value is 0, the footer transistor is off. So, the PDN, that is the pull down network is disconnected to ground, which will prevent my leakage current. So, that is there is no path from VDD to ground. So, what happens during the evaluation phase? So, during the evaluation phase, the clock value is high. So, the footer is always on, allowing the PDN network, that is a pull down network, to connect it to ground if a discharge path is established. That is if A value is 1. Okay, what is the advantages of this footed dynamic CMOS? It will reduces the leakage current and it will improve the noise immunity, as the PDN network is disconnected from the ground when it is not in use. So, let us discuss about the disadvantage of this logic. It will add an extra transistor, that is footer transistor, which will increase the circuit complexity and slightly slowing down the operation due to the increase in resistance. So, let us discuss about the logical effort of footed dynamic CMOS logic for an inverter. Okay. So, for inverter, you have to connect one transistor, right? That is A. So, you can see how to size the PMOS means for PMOS, it must be always 1. Okay. And since I have two NMOS transistor, so 1 plus 1 is 2, right? So, A value is 2 and the footer transistor value also 2. Okay. So, in order to find the inverter value, logical effort of the inverter, that is termed as GD, because I am going to calculate only for A, right? So, the A value is 2 here and the inverter value is 3. So, 2 divided by 3. So, this is a logical effort of a footed dynamic CMOS logic. So, now let us discuss about the 2-input NAND gate. Okay. So, I need to find the logical effort. So, you can see here A and B is connected in series and for PMOS, I told you it is always 1. Since 3 NMOS is connected in series, it values 3. Okay. So, if I want to find the GD value for A transistor, it is 3. So, 3 divided by 3, that is equal to 1. So, this is how we have to calculate. Next, let us discuss about unfooted dynamic CMOS logic. So, here there is no footed transistor, you can see, and there is therefore the PDN, there is pull down network is directly connected to ground. So, during the what happens during the evaluation phase? During the evaluation phase, if A value is 1, the output is connected to ground. Otherwise, it won't. It will be open circuited, right? So, during the pre-charge phase, if clock value is 0, and output is connected, the VDD is connected to out, right? So if suppose the A value is on, A value is 1 means there will be leakage current that will flow from my VDD to ground, right? So the advantage of this circuit is the circuit is very simple, as there is no extra transistor, and this will reduces the propagation delay slightly because of reduction in the transistor. And the disadvantage is it will has a high leakage current due to the pre-charge phase, and it will reduces the noise immunity as the pull down network remains connected to ground even when it shouldn't evaluate. So let us discuss how to calculate the logical effort for an inverter for uh, unfooted dynamic CMOS logic. So you can see the PMOS value is always 1, and for A we have to connect 1. So what is the GD value? GD value is equal to A value, that is 1 divided by 3. So if you calculate the logical effort for the 2 input AND gate, so the clock value of PMOS is always 1, and since I have 2 transistors connected in series, that value is 2. A value is 2 and B value is 2. If I calculate the value of GD is equal to 2 divided by 3. So 2 is the value of the A or B. Okay, either you can use it. So 2 divided by 3. Okay. So the application of this unfooted dynamic CMOS logic is it is used in simpler design where the speed is a higher priority than leakage concern. So let us discuss the difference between the footed and footed dynamic CMOS and unfooted dynamic CMOS. The first difference is foot transistor. So here the foot transistor is present because it is nothing but footed dynamic, right? So here it is present and here it is absent. And noise immunity. So noise immunity is higher. Here it is low. And because I have a footed transistor which will prevent the leakage, right? So the power consumption is higher, slightly higher compared to because of one more transistor, right? So it is lower and the speed it is slower. This is faster and this in compressed is higher. This one is lower. So if you compare the dynamic footed dynamic footed dynamic the G value for inverter. So inverter G value, and for n input AND gate, what is the G value? G is nothing but logical effort. Okay. So what is the formula? So here it is, the formula is 2 by 3 and here it is n plus 1 by 3 for n input NAND gate. So this is NAND gate and this is NOR gate. NOR gate it is 2 by 3 G value. Okay, for unfooted or it can also footless. Okay, footless dynamic, it is 1 by 3 and this is n by 3 and this one is 1 by 3.